So I'm going to be talking about three different things. Sunfish management for Lustre on-demand fabric attached memory file system. There's a bunch of people working on it, and from different organizations like Sandia, WAM Cloud, Open Fabrics Alliance, and CXL Consortium. I'm going to be talking about goals and motivation for open source Lustre on-demand file system. Composable disaggregated infrastructure, I'll be giving you kind of a tour on that. And then Sunfish Composability Manager for CDI on HPC systems. And then I'm going to kind of bring everything together by combining Lustre on-demand with Sunfish to create a dynamic burst buffer for use on HPC systems. And then I'll give you some further links and take some questions and answers. On-demand community-based Lustre burst buffers. A lot of people have been working on Lustre on-demand, different places. Some of the code's not in the main tree. So part of one of the motivations for doing this is to get into the main tree with community Lustre burst buffers. And then also part of the motivation is to bring in and start using Lustre for parallel burst buffers, and then also integrate it with CDI, and then bring in new infrastructure so people can come up with new ideas to start utilizing some of this infrastructure. Why now? Why is this kind of a different setup than what's being done on some other systems? We're talking about using it again, the tree, adding into the Lustre tree, Lustre on demand, and then also taking advantage of the ephemeral nature of burst buffers and combining that with CDI and CXL, which is coming down the pike here very quickly, and then also centralizing management of that kind of implementation for HPC systems. That's important to it be scalable, and I'll go through that a little bit. And then give some use case examples of what we can do with that kind of a setup using, again, like I said, Compute Express Link and Sunfish. So part of this is the main initial part is Lustre on demand. We want to bring an on-demand parallel file system in for burst buffers, and we want it to be based on Lustre. And so you have to bring up your management, your metadata, and storage in order. But you have to do it in the right way and at the right timings. I've been working with burst buffers enough to know that. You also want to be able to, if you need more storage OSTs, you can bring those in. That's kind of a nice feature with the on-demand file system. If you got a high demand load or you want to add more stripes, you can bring in more OSTs. You can also, if somebody wants more MDTs and OSTs, I've done this before, you can allow in the underlying infrastructure for the burst buffer, you can actually allow people to customize their MDTs and OST quantities so that they can get more of their more MDTs or OSTs as they want. And then another key part of this is we want to implement, so right now we're using Z pools and LDisk FS. We want to come out with a new RAM disk OSD. That'll give us the ability to simplify it's ephemeral that we're playing with the burst buffers, so we don't need all the logging that we're doing. We don't need aggressive logging. We don't need things like a lot of checkpointing and things like that. So we want to take and strip out things that we don't need. We want to be able to stage in and stage out your data when requested. That's part of the CDI options. And then we want to have local caching if somebody wants to do that later on too for implementations. Why a burst buffer? That circle on the right side kind of shows why. If you have a localized file system, instead of a shared file system, you get the performance stays pretty flat and linear based on demand because you're the only person using that file system. How you get that to work is you have to bring in and stage in your data. So you're bringing the data, and then you do your computations using your local parallel burst buffer, and then you have to stage the data out. So a RAM-based OSD, a little bit more details on that. We want to skip block I/O aggregation. We want to be able to handle small file I/O. We want to be able to, we don't need to provide support for data recovery. We don't need to be, like I said, we do aggressive logging. We know as soon as the file systems, we're done with the file system, we're going to delete that file system. How we get the burst buffers implemented, I've done this already. So normally what you do is you allocate nodes on using Slurm or Flux, for instance, or Kubernetes, and then you get those allocations of nodes. Then you start the file system. Then you get the data input. Then you actually run the job. Then you copy the data off. Then you have to manually stuff the file system. What I've been able to do using, like for instance, Slurm Prolog and Epilog is actually take, because those are already running parallel on the nodes, all you have to do is tell the nodes what they are in the allocation, and they can be, for instance, in my case, usually what I do for simplicity is use the bottom node for MGT, MDT, and OST, and the rest of them are straight OSTs, and everybody's sharing that same parallel file system that's in your location. So what happens is it becomes a simpler operation because you're using the parallel capabilities of the Slurm Prolog or Epilog in this case. So you get your allocation. Your burst buffers file system is started automatically. It takes usually about 10 seconds to start up, and then you just have to stage in the data, run your application, stage off the data, and then when your batch job is done, it automatically deletes the files. It deletes the OSTs and MDTs and MGTs. That they just go away. And in that case, because they're being deleted, you don't care what they are at that point. So composable disaggregated infrastructure, what I'm wanting to do is using CXL in this case, I want to take memory from a shared pool. It would be on, typically on the top of a rack. I'll kind of show you that. And then you'd attach it with a fabric, CXL in this case. And then you augment more basic nodes. There's some advantages to that. But one of them is I can dynamically add in more OSTs as I want to. So if I want more OSTs, I just attach them in. Dynamically attaching more fabric attached memory, I can do that too. I can take memory from a shared pool, augment a node with that. And if I need more memory for a batch job or whatever, I can add that memory in right away too. The problem is when I'm doing a large cluster is, and with a lot of pools of memory and stuff, I have to control those. So if I have a lot of racks and I've got a lot of nodes and a lot of memory I'm trying to share pools of memory out of, then I need to be able to centrally control that, and it has to be done in such a way that I'm not doing a lot of traffic transactions, and I can maintain consistent operation on the whole cluster, because I'm planning on doing all these virtual things. So what we're talking about doing is Sunfish. In this case, Sunfish has been a project that we've been working on for a few years. What we do is the clients are on the left side. They'll make a request to Sunfish. They'll make a request to the composability manager on Sunfish. So that part will evaluate what the request is from the client. So if it wants memory pools that it wants to augment nodes with, you can decide where those pools are and so on and so forth. Then it goes to the core, which acts as a database and also controls the main operations for the CDI. And then it acts as what I would call a truth, library of truth. Everything that's being done in the machine is recorded in that Sunfish core. And then they'll make commands over to the hardware agents on the right side. We'll see we have CXL agents, Gen Z agents, Slingshot, Omnipath, and everything else. And then those actually make the associations with the hardware. And then that all gets brought back to the left side through events, verifications that, hey, I've got what I needed assembled, and kind of works from there. A few people working on that. The composability manager reduces transactions to the Sunfish core because we've got to scale this thing out. So it provides decision making for the, like I said, for the clients. It'll say, hey, is this available? Or this is available, this is your best option. And then once it's done, it verifies the burst buffers are created. And then we do our stage in and stage outs with that too. We allocate, in each pool of node, we can allocate hardware based on the top pools. So in this case, we've got color-coded nodes with the associations to the hardware on the top. So we've got memory pools on the top of the rack, and they're augmenting the nodes underneath for the fabric attached memory. And then we're using those for the burst buffers. So we're talking about making those decisions using reinforcement learning. It provides a fairness and also penalizes bad ideas that we would try to implement. And then we want to verify that we've got the associations made for all the batch nodes that we do for the burst buffers. So we go active, pending, and free. With lockouts, we'll say, hey, we got memory that we want to allocate, and it'll lock that out, and then until the associations are made, and then it'll keep that locked out until it's done with it, and then it'll release it. We've been talking about using Flux and Kubernetes for the new generation systems. Flux has an engine, a CLI, and agents. We can use the agents to help us do our stage-ins for the burst buffers. And also help us make the associations for the CDI part of the operations as well. And then Kubernetes has their own version with pre-filter, pre-bind, and bind. Bind makes it available for the pods that you use on containers. And then the batch jobs, of course, would be made available on Flux using the Flux engines. So currently, we're doing a lot of stuff with backflows on our schedulers, and with the CDI implementations, reinforcement learning, and the burst buffers can be made basically more dynamic. We have more options available. So if we got pools of memory over here, we can take those over and use them for a different machine at different times. Gives us more, so we're not just doing straight backflow strategies. We can do more dynamic scheduling as well, because we can control the schedulers. I talked a little bit about the burst buffers. I've been working with them for a while. What I've found again is that I can allocate the burst buffers, like I said, using Slurm, Prolog, and Epilogue, because really those are parallel and they're going to touch every node that's in operation. The other part is if something fails, it'll drain the node out, for instance, so that you can have somebody go back and take a look and see what failed. If it's a bad hardware issue or whatever, it's drained out, so you don't try to reuse that same node. There's a couple different advantages to it. We've been doing, like I said, prologues and epilogues. So the prologue would go through and it would do a question. It would say, what kind of a node am I? I'm at the lowest node in the allocation. From the lowest node in the allocation, then I become the management node and the metadata node. And then on my implementations I've been doing, all of them are OSTs. So, and then I use a custom start script, and that allows me to add the versatility if I want more management nodes or more OSTs, or I can, metadata nodes and OSTs. I can make those adjustments there, and it makes it simpler to call it from the Prolog too. So it's a simpler operation. The Prolog just says, okay, here's the parameters, and it sends it to the custom startup script, and then that's how it gets deployed. Once I'm done with the allocation, the epilogue goes through and it unmounts to an unprovisioned state and releases all the nodes. In our case, it would also release a CDI. But then I don't care on the stop script who's been the management node, who's been the metadata node, and who's been the OSTs, because it doesn't matter. They're going to go away anyway. So I just wipe them. Dynamically attaching, there's some use cases here. Like I said, if I wanted to add more memory from a shared pool, then I can, let's say I've got enough memory, I don't have enough memory to run the batch job I'm running, and I'm bogging down the system or whatever. I can add more pools, memory from the pools, spread out that file system a little bit, and then if I need to add more OSTs, I can add those in as well. Further links, some of the stuff's being done, some of it is in flight, and we're trying to build on some people's ideas here too. So, do you guys have any questions? I went through a little bit.
Kevin Harms, Argonne. So Michael, for the Lustre on Demand, are you using, do you have a pool of storage hardware that gets allocated, or this is getting, you basically just have a big cluster and some are compute nodes and some of those get allocated as storage?
Yeah, so what we've been doing initially, I'm planning on doing initially again is starting with regular compute node hardware and allocating out of the RAM using RAM file systems. Then later on, because I don't want to steal resources from the machines if I don't need to. So what I'll do is I'll pull it from the pools of memory on the top of the racks later on as they become available. So.
Hey, Michael, for your RAM-based file systems, in the earlier slides, you mentioned CXL. Is that where you're using the technology underneath this to create your RAM-based file systems, or are you actually using main memory? I was just curious why you mentioned that and if that's being used here.
So the idea is, and I kind of glossed over it, was you start right now with the main memory on a compute node and just allocate memory out of that. CDI gives us the ability to augment the nodes. And that gives us a lot of advantages. First of all, right now, I think I read a paper where they said 80% of the batch jobs are using not all the memory that's in the boxes. So we can reduce the footprint of memory in the boxes, augment them using CDI to make them appropriate for the batch jobs. But the other thing is, in our case, is we can actually take that and build our burst buffers, which are IO based, out of that CXL attached memory. So, and CXL3 gives us security and also the ability to share pools out of the same memory. So, yeah.
Sorry, James Simmons I'm so loud, I'm sorry. From Ornell. So do you have plans to push it to the WAM Cloud, the OpenFS branch, the OSD?
I think so. As long as it's allowed, I want to. That's my intention. So. Just to make it all open source and in the tree. So.
Do you have any other questions? Let's thank our speaker again.